Anyways, very happy to be here. So again, I'm Justin Morrow, and this is actually my first time coming to Amic, and I really only knew that it existed starting about, I don't know, a couple months ago. So I'm really learning a lot, and learning that I should have known more about this before, and kind of glad that I'm seeing it. So I'll dive right in. What I really want to talk about is just all the work that we've been doing at a high level in laser polishing in our lab. I'm currently a postdoctoral researcher under Professor Pfefferkorn, and I just graduated from the lab about a year ago in the material science program with the topic of the phase transitions and property changes that happen in steels when you're doing micro polishing like we do. But now, and why I'm really interested in being here, the longer I'm here and learn more about it, is this year of work is really about commercializing our process. So we have a lot of understanding about how the process works, but there's still a lot of room to learn more things to get to where someone in industry would feel comfortable actually applying this process and seeing the value. So we're answering a lot of these questions that'll help us really bridge that gap between something that produces a lot of papers and is very interesting on paper and something that's really applied widely in industry. So just to zoom out a little bit, whenever you're using a laser for modifying the surface, you're usually starting with something rough and trying to make it smooth, or something smooth and make it rough. And you can either do that by melting the surface or by trying to actually vaporize it. So that'd be the ultra-fast lasers or things like that. So the area that I've highlighted in the top left, the remelting and smoothing is really our area, our core. And even further within that area, you can look at it as a micro scale or meso and macro scale, metals and non-metals. And so our core right now, and for really several students before I even got to the university, was micro scale polishing of metals using remelting. And we're continuously looking to grow that area, but that's really our core. And so in this area of polishing of metals, just on the right, the most studied areas are steels, titaniums, and nickels, and that's true with our group as well. This is kind of where we started, and the graph itself is a representation of the roughnesses that various researchers have tried to investigate. So up at the top, you're up at like 15 micrometers RA, a standard roughness metric. Down to the bottom is 0. So ideally, you want to take something that's as rough as possible and make it as smooth as possible for the best polishing result. So if we look a little closer down near the bottom, and so now the scale is just from 0 to 1 micrometer instead of 15. This is where, if you put on the standard for what is a mirror finish, right, what's the ideal, you're down here below this 0.1 micrometer RA. And there are several different finishes. This is just one. But you can already see that a lot of these haven't reached there, and so there's a lot of room for improvement. And a lot of that has to do with just how far you're stretching, how rough your sample is to start. Now for us, working at the micro scale, we tend to start with something that's 200 to 400 nanometers RA, and then try to get it down below this mirror finish. So working at the micro scale, which is kind of our core. And now for us, achieving this mirror finish is important, and a big driver for us is always pushing for rougher and rougher surfaces and maintaining that level of final smoothness. And really, we have kind of 3 core things that are important to us, right, in doing this. So it's to, for university, it's to have a scientific understanding of the process and the physics and how it all works. But we're also an advanced manufacturing lab, so what we really want to see is someone on a shop floor be able to apply this. So while we'd love to run models and then tell someone else what's interesting about laser polishing and all the things that can be done, we really want someone else to be able to model this and have fairly intuitive and fast models. And then always to optimize, use our knowledge to get better surfaces and then maybe get new predictions, not just about roughness, but other things, and I'll get to that later. So first I just want to step through what we've learned over our years of research about pulse laser polishing. So the basic setup that we use is a near-infrared laser that's pulsing in the nanosecond to microsecond pulse durations in kilohertz frequencies of pulsing about. That's controlled by a computer and a control card, a scan head to move the spot, and then a stage. So a fairly simple research setup that's still, we're always adding it and trying to get it closer to a commercial setup so that, again, bridging that gap. And then we'd start with controlled surfaces. Here we have a micromill. We've also looked at ground, several other, even an acid etched, just different metallic surface finishes. And then we would, we can play with a lot of parameters in our setup, the power, the pulse duration, the pulsing frequency, and things like that. So this is just one, just the pulse duration. And this is one that we've found over time that's really critical in changing the physics of what's going on during a single laser pulse. So here, we have 3 images of measured pulses crossing from the nanosecond to the microsecond. And so what we found is that as we increase this pulse duration, first you get, starting from the rough surface in the top right, and now having a laser polished surface here, at really short pulses in the nanosecond range, you do a lot of smoothing. You're kind of, blurring everything together, but you can still see the longer features that are left over. As you increase that pulse duration, those are really gotten rid of very effectively, but you're starting to introduce these new ripples, new features that you don't really want to add. And so we've tried to understand and predict both of these things. So the understanding for the smoothing, we've kind of modeled it as when you start with a rough surface, it's initially solid, but you have some surface topography. You very quickly make that liquid, and now you've freed up this rough thing to try to smooth itself out under the surface tension. It's trying to minimize energy. So we've modeled it as a damped oscillation, and so you can define a critical frequency of which high frequency features are smooth and what low frequency features are not. So this just is derived from oscillation theory. The ripples, we did some multiphysics modeling of Gaussian laser pulses on a surface, and that showed that at these longer pulses, you develop a temperature gradient in this melt zone. So not only is it melted and oscillating, but as it's melted longer, you start to drive it towards the outside. So that takes some time. So the graph here on the left, you can basically see that there's a short amount of time way on the left side where there's no flow, right? And that height will increase with time. And so this just reflects what we observed, where short pulses don't seem to add anything. They smooth out, but not perfectly. And as you go longer, you get more smoothing, but you add these. And so our current understanding of the process, and I hope the animation is working, we'll see, is something like this, where you have a laser. Initially, it smooths out, and then because of the long pulse duration, you add additional features. And that's our current understanding of how the process works. But we also want to have predictive models that can be exercised and tell us more about how to, what to do about this or how to use it. So the capillary smoothing model uses that critical frequency, and then since this is telling us that the high frequency features are damped and the low frequency are not, it's fairly straightforward, intuitive, to use a high pass or a low pass Gaussian filter to model this. And so we can take a surface, use a Fourier transform to put it into the frequency domain, apply our frequency-based filter, transfer it back, and then we have an output. And so we can then measure the roughness on this predicted surface, and we get to about 10 or 20% error, a good prediction of what's going to happen. Now, the important thing about this model is that it predicts that as you increase your melt duration, it will only get smoother, which gets us back to the ripples that we observed. So we can't, for every condition, do a full multi-physics finite element modeling of the fluid flow and temperature gradient. So what we did is and there's a long paper behind this equation, that I don't want to get into, but we did an analytical derivation of a simplified metric for what we call a normalized average displacement. So for a given condition, a Gaussian beam of known power and radius, about how much material will move and how far it's going to go. And then what we found is that if you have this metric, and then you do tests of the surface roughness, so here the vertical axis is a measure of the roughness, the height of the features left over, and the horizontal is that predicted normalized average displacement. There's a fairly linear relationship between this experimental result of the feature height and this analytical prediction, which lets us get to predicting the shape of an individual laser spot. And so that's nice because what we can do is we can geometrically overlap those spots to represent the final ripple pattern that you'd have based on how we're moving the laser spot around the surface. So we can just put in whatever overlaps we're choosing and make sure that that's going to match up well. And so now what we have is a model that incorporates the smoothing that we had originally, but also these ripples. And so it doesn't predict now that with longer pulses you're just going to get smoother, but that there's some trade-off, which is much more reflective of reality. So again, with this model, we're to about the 10 to 20% error range, which is we're fairly happy with since we have to make a lot of simplifications or assumptions to make this simplified version work. And then, with these models, obviously, we're always trying to optimize the results using our knowledge and to get more predictions based on this core area. So one of the ways that we've tried to optimize this is moving away from the one-pass only model. So here I'll go ahead and use this. So this here on the far left is a rough surface, fairly similar to the micro-milled one that you saw before. And if we use the short pulses, so in the nanosecond range, you get this third one, which you can see kind of blurs it together, but you can still see the outline of the original surface features, which is obviously not ideal. And it has gotten smoother, but it's only gone from 172 down to 152. So if we increase the power pulse duration, we can get to the thermal capillary, and now we've gotten rid of those features, but we still have a lot of ripples left over. And our smoothness has gotten a lot better, so now we're down to 86. But these ripples are really not ideal. So what we did is combine these two. So we have the thermal capillary regime is our first pass, because that gets rid of everything that was there before. And then we follow up with the capillary regime, which does a good job of blurring things together, but doesn't get rid of large things. And we get a much better result of something that's now under 50 nanometers RA. So we're trying to utilize the strengths of these two processes. One is much better at knocking down what's there, and it leaves high-frequency ripples that are much more amenable to further laser polishing. And then we can follow up again with a second pass with different parameters that can get rid of that. So this is already fairly effective at predicting overall steady-state surface roughness. But really what we want to do is look at other effects. So the effect of the beam diameter, curved surfaces, angled surfaces, sharp edges. And so we now, after many years of work, have models that are flexible enough that we can try to get more out of them besides this steady-state ripple. So this is just one example. And so I forgot to add the sizes here. But so this is a 30 micrometer spot. This is 100 micrometer. And this is 200 micrometer. Now, that's the laser spot, not the melted area. So I think it's a little closer to 15, 60, and 160 for the actual melted diameter. So what we found in this published work, which is from 2014, I think, is that at the time, we saw that this small one doesn't really get rid of the roughness, right? I mean, it's still tracking with the surface. You can see that it's a little high here being yellow, and that kind of travels all the way across. The blue travels across. As you increase the beam diameter, you definitely start to get rid of the surface that was there originally, but you can still see that while this high part now is kind of, tracking across the laser polished area, it's still there. It's been shifted, but it's not actually gotten rid of. Whereas if you get to a large enough beam, it really looks kind of decoupled from the surface that was there originally. And so when we exercise the model, we see the same result, which is, well, was for me when I saw it pretty exciting, since this is from this summer and this is from 2 years ago. Another thing is that all of this has focused on this steady state ripple area in the center, but you always have edges of these polished areas, and you can actually start to get these sort of form or waviness errors that you certainly don't want to introduce. So knowing that your result in the center is actually going to be a little different than your result near the edges, we can start to look for strategies for, this is constant power, so maybe you shouldn't use constant power at the edges, you should change it a little bit. To get rid of these sorts of effects. So it's just new things that we can use the same model to predict, to leverage it. And there are lots of other things that we're still working on, but these are very new. So I think that's all I really wanted to talk about today. Just wanted to thank our collaborators over at LASEX who are working with us on these projects, and Frank and the other people in the lab. So with that, I'm happy to answer any questions. So, yeah.
Are there any subsurface effects when you do laser polishing?
Definitely. So I think one of the biggest open questions right now is residual stress and hardness. And that's where things like there's a lot on the meso and macro scale, and so my PhD work was really re-looking at that for the micro scale. And so what we found is that the hardness varies fairly widely, and that how you're overlapping it makes a big difference in terms of whether you're back tempering or not. So it's, especially in steel, you quench it. So each laser pulse, because it's surrounded by a giant heat sink, is just quenched, and then now you're reheating it with all the subsequent passes, and it matters how it's being overlapped. So there's really a lot of opportunity, it being a thermal process, to tailor your microstructure as well. But that's still an area that requires a lot more work for understanding for various alloys. Yeah. Oh.
Are there any applications in industry where this is used at all, on a very, very small scale?
Oh, I mean, so laser polishing is done. It's just that I think, so this year was the second year for laser polishing specific conference, so it's still growing. And so a research group in Germany, Fraunhofer ILT, has their like 5th generation of laser polishing machine or something, I think.
So to my knowledge, there's no laser polishing, commercial laser polishing that's talked about in public. But I've heard from companies that they've been using it for a while in-house, but don't tell anybody about it, like Apple. So, now, I don't know anything about the materials or the scale or whatever. In the public domain, there's the group in Aachen, Germany, that's been working for about 10 years, like us, on it. They've been focused much more on developing equipment, like machines to do it. We've been focusing on the process and predicting it, and are now working with LASEX in St. Paul, Minnesota, because they're the experts on integrated lasers and building laser setups, right? So we're letting them, or they're leading the commercialization part, right? And we've been, Justin mainly, trying to help, okay, what other questions do you need answered, and where do we need to get the model to so you can sell a product,
Right.
right? Hopefully by the end of next year is their goal, to get the first laser polishing systems sold, maybe delivered, I don't know, but at least sold. So we're helping them with that. So it's been used, but unfortunately I don't have any details as to whoever has used it have done it entirely in-house.
Okay.
You're probably restricted in your wavelength, right? But would you expect any change with changing wavelengths?
In the overall results? So, I mean, the absorptivity changes a lot. So for metals, I mean, I think short wavelengths are actually often better, higher absorptivity. We're working with metals with an absorptivity around like 30%, 40%. You can certainly push that higher. I think where it's most important too is when you're starting to get into non-metals. I mean, every new material that you're going to try and polish is going to have a very different absorptivity. And so that's where it's really a material laser pairing is really important. So that's critical, yes. I think for us, we could change the wavelength, but really we'd just be mostly changing the absorptivity unless we start playing a lot with the diffraction limit of the of the focus, and that's part of why we're not even close to diffraction limited. So the wavelength doesn't matter that much there.